Okay, so last time we were getting through the x86 assembly, right? So when we covered the like memory instructions, which allow us to move from memory to the registers and between the registers and also back to memory. Then we talked about arithmetic operations and we covered conditional instructions as well. And we ran out of time. And what happened is that we said, okay, look, we looked at this stack and then we said, we will continue today with function invocations. So, okay, just a quick recap, right? So this is approximately where we stopped. So we looked at the stack. Essentially, stack is just an area of memory which is pointed by the special stack pointer register, right? And there is a couple of instructions which allow us to maintain the stack. But let me ask you a question. So what do you think is the main purpose of the stack? Why do we need it altogether? So who can tell me? Procedure calls, exactly. So, and do you know why? Yeah, function calls. Okay, so good that you know, guys. Okay, let me just quickly tell you what's going on. And maybe we covered it last time. I a little bit forget. So the main point for maintaining the stack is to be able to return from functions. So in this example, we have function foo, which we call from two different places, right? So from two different branches of the if then else statement, right? And obviously when you call it from here, right, from this location A, right? The idea is that when you return, you want to continue executing at this point A, which is right after the function, the next instruction after the function, right? And if you call it from here, from B, right, you want to continue executing after you return from the function, right? Exactly from this next instruction after the call foo, right? So how can we do this? So what we do is that we push this value, this address of the next instruction on a stack, right? So essentially, if you have something like a call foo instruction, call foo, right? And this is next instruction after foo is at address A. You have stack right here, ESP. In my example, stack grows up. I mean, up on a figure, but towards the address 0 in the address space. This is 0. This is max, right? And what happens is that at this point, when you invoke foo, this address A is placed on a stack, right? And then you jump to the label foo. So inside, you start executing the label foo. So what is label? Label just an address, right? After you compile and link the code, right? So you execute all instructions inside foo, and then you do the return instruction or ret. This ret instruction, of course, when you pushed A on a stack, right? The stack pointer is currently will be pointing at this location, right? Right at A. When you do this return instruction, the return instruction picks up this address from the stack, right? Changes the ESP to point back to this location, kind of like forgetting about this A, and jumps back to A. So essentially it's a jump here. And then you continue executing right after your original invocation, right? So this is the main point, main reason to have a stack, but there are some additional reasons and we will cover them today. So, okay, let me illustrate it again with this diagram. So the main purpose of the stack is to store the return address for the current procedure, right? So again, in my example, right now, ESP is pointing here, stack will be growing this way. EAP is kind of pointing to the call foo instruction, right? And when this instruction is executed, what we place on a stack is the address of the next instruction. And how do we compute the address of the next instruction? It's the current value of the instruction pointer plus the size of the current instruction. So maybe this is 4 bytes, maybe this is 5 bytes, right? And instead of executing next instruction, right, the call redirects us to label foo, right? So it changes the instruction pointer, similar to how instruction pointer is changed by jump instructions, right? So now we start executing within foo, right? Of course, stack pointer gets also changed, right? Now it's pointing right here, right? So this is the address, which was A in our previous example. We execute all instructions within foo one by one. When we reach the red instruction reads the address, which is right here, which is effectively a pointer to this address, right? To the address of the next instruction right after the call instruction. The instruction pointer is changed. So we start executing this next instruction, and the stack pointer is also changed. So we kind of forget this value, which we pushed on the stack. So this is how the function invocations work in general. So the two instructions are call and read, right? And the stack is involved because it keeps the address of the return. It keeps the return address on the stack, right? So let me stop here for a second. Like, I'll wait for questions. Is this clear how this works? Clear. Any questions? Do you understand how will it work if we call the functions recursively, right? So essentially the mnemonic for these two functions is, for the call instruction, not two functions, but two instructions, is it makes an unconditional jump to a subprogram and pushes the address of the next instruction on the stack. So effectively it's equivalent to push the value, which is instruction pointer price size of call instruction on a stack, and then jump to my function, right? So you can think of a call instruction like this. And the read instruction pops off an address and jumps to that address, right? That's what I said before. However, stack can be used for other reasons as well. So it can store local variables, and we will cover today what these local variables are. It can be used for parameter passing inside the function, right? So some arguments can be passed in registers, but some can be passed on a stack. It depends on the calling convention, and we will cover calling conventions today in the second lecture after we finish this first one. And sometimes, you know, when you're running out of registers, right? So you can push a register on a stack. Why is that? Because imagine you want to do something like, you want to add something in, you need to do an addition, like compute the new value, something like EAX result of some other register. But imagine you already have something useful inside the EAX, right? Some value which you computed just maybe here, right? Previously in your program, and you don't want to lose this old value. This is old. You say, okay, so what can I do? Imagine you all registers have some useful values. So you don't really have a temporary register to place here instead of in place of EAX. So what you can do is you can push the current value of the EAX on the stack, compute the new value of EAX, use it, and when you no longer need it, you can pop back this old value, which you saved here. You can restore it back in the EAX register. And you can use a different register. You can use EBX here. You can use any of the general registers. The fact that it's EAX is just like an example. So, okay. So what I wanted also to make sure that you guys understand how this call invocations work in case of recursive functions, right? So let me just quickly cover something. Maybe I will have example later, so no need to cover here. Okay, so there is a couple of instructions which can manipulate the stack. I mean, first of all, you can always do something like move into the area of memory which is pointed by ESP. Do something like move the value of EAX into the area which is pointed by ESP. So essentially, this will just like, hold on, it will move here, right? You can also change ESP, right? You can move something like, you can increment or decrement or sub or add something to ESP, right? So you can say increment ESP by 1 byte, but it's like rarely use 1 byte values these days. That's why increment and decrement are on pointers are rare. But you can sub, for example, 4 bytes, or you can add 4 bytes, right? And if you sub 4 bytes, since the address 0 is here, right? Obviously, ESP will change here. If you save something over here, then this will become your next stack area, right? But there is a couple of instructions which help you to deal with the stack as well. So one of them is push. Let me just clear everything on a slide here. So what it does is the following. So if you're currently trying to execute a push instruction, which pushes this value bar on the stack, right? Why is it a bar? Okay, whatever. So what happens at this point is that you obviously instruction pointer will go to the next instruction. It's not a jump. The value of bar gets placed on a stack, right? And ESP gets changed by the size of bar. So it's essentially, it's kind of like moving to ESP and then sub 4 bytes in this example from ESP, right? So we inserted data on a stack. And there is a similar instruction. Let me just switch to chart so I can see it. In which you do the pop instructions. Essentially here in this example, ESP is pointing right above, right under the bar, so or right at bar because addresses grow this way, right? If you do pop EAX, the ESP will change, right? And the value of EAX will change as well. So essentially EAX will get the value of bar. So the value of bar, actually, it doesn't disappear. So it stays here. It just kind of, it's no longer pointed by the ESP register. So if you pop something again, you will obviously pop the value, which is right here. So whatever it is, it's like B, for example. If you do pop EBX, in this example, ESP will change like that, and EBX will get the value of B, right? So, but nevertheless, those are convenient instructions, right? And at this point, this is essentially the end of this lecture. Let me stop here for questions. So what we've done, just a recap here, we covered the core of the x86 32-bit assembly, which means that now you guys, you can actually read the assembly code, and we will take a look at real examples later today. I will compile some piece of code. It just makes sense to do that after we cover calling conventions, which is our next lecture, right? And you can you will see that the compiler, the C compiler will generate the assembly code, which you will be able to understand. So it's kind of natural. So like despite all these optimizations which are done, often you can read the assembly and understand what's going on. So that was the point of this lecture. And later on in this class, obviously, since not all things can be expressed in C, right? So some of the things which you will need for building operating systems, you will have to write directly in assembly, like setting up the control registers on the CPU, doing the context switch where you have to precisely save all the registers, flip the stack pointer, and restore the registers of another process, right? So we'll get there. When you handle the interrupt, for example, again, the lowest bits of the interrupt handler you will have to write in assembly, just because the C doesn't have a way to express saying that I understand what this interrupt calling convention is, right? So that's essentially what you learned up until now. And I think it's very useful knowledge, because not being afraid of assembly is a great skill, right? So let me stop here. Are there any questions?
Can you go back to the previous slide?
Yep.
If you didn't pop EBX, the ESP would be pointing at the upper red line, right?
Let me just illustrate it one more time. So ESP is changing by the size of the pop argument. Let me erase everything here. So let's just do the first pop, right? So note that this is address 0 and this is max address, right? So stack, when people go grows, when people say stack grows, it means that the call instruction, for example, will push something on a stack, and the stack pointer will be changed moving this way, right? So if I would do a push, the push would save something right here, like, I don't know, who, right? And the ESP would be pointing here. That's the behavior of push. And behavior of pop is opposite, right? So essentially, if I pop like I do in this example, this value, which is right above the stack pointer, I mean, if it's a more conventional drawing where it's not a vertical but a horizontal address space from 0 to max, right? The stack will be growing this way, right? And if your stack pointer is pointing right here, the pop itself changes the pointer here, right? But reads this value, those 4 bytes, right? Is that what you were asking? Because I wasn't sure exactly that I understood the question, but I kind of was trying to guess.
Yeah, I'm just trying to clarify that. I get it. Thank you.
Okay, yeah. And that's important. So this detailed understanding of what happens to memory, and essentially that's what confuses people in this class. But it's not so. It's kind of easy, right? So you'll get it. Just you have to see it for a couple of times, and you will see more of it today. Anything else? Let me switch to chat if anything is there. Okay, good. We're ready to go to the next lecture. Okay, this is, oh, I didn't see this, the transcript. I'm sorry, so I apologize. So like someone requested to, whatever, do a subtitles for my voice, and I just only now I noticed that it was a request, so sorry. Okay, so on to the next lecture, which is even more fun. So this lecture is all about functions, invoking functions, and essentially something, a convention, which is called a calling convention, a convention about how the arguments are passed into the function, who saves and restores registers, how arguments are returned or return values are returned from a function, right? And stuff like that. So, right. So that's a useful knowledge as well. It's really not part of the operating system class, but I have to cover it because many people just don't know what's going on. And then it's very hard to build the process, because when you build the new process, you have to pass arguments on a stack. So you have to construct this stack according to the calling convention. So, because imagine you do the exec, right? So you exec something like, hold on, let me just enable the pen here. You're doing exec bin WC, but imagine you're passing some arguments to WC. Imagine you want to do an invocation, which is like -L and maybe a file like foo.txt, right? There is a way to pass arguments in exec, right? And those arguments will be passed on a stack. So there will be, later on, we'll understand how like they will be constructed. Remember this arg array, right? Which has the variable number of arguments which are passed to the main, right? So when you construct the process, you have to construct those arguments on a stack. So you have to understand it. But okay, we'll get there, not right now. So since we just covered the stack, we can safely skip this recap about the stack. And we already know that, okay, stack is the thing which allows us to call functions and return from them. If we had a gap, that would be useful to remind, but right now, all good. So this is the example which I was looking for just 10 minutes ago. Example when we are invoking a function recursively, right? So in this example, there's a function foo. It takes an integer argument, and if the integer argument is 0, it simply returns. If not, it just decrements the integer argument, right? And then it calls itself recursively, right? And eventually returns. So I just wanted to illustrate again. I'm pretty sure that this is very easy, but I still wanted to go over it one more time. So imagine we have a stack, and I will be drawing it similar to how I was drawing the stack before. So it will be growing this way, right? So this is 0, and this is max address of your address space, right? So imagine we call it with 4. Okay, let's just do 2 because 4 will take us forever. Imagine we call it with 2. So we pass a as 2. Obviously, it's not 0. We decrement a and invoke foo as 1, right? At this point, wait, hold on. Even here, when we just called foo, there was a label, imagine a here, which is the next instruction after this foo, right? Even when we invoked foo for the first time, a will get placed on a stack, right? So essentially a will be here and ESP will be changed to point right here, right? So this was ESP is in time 0. This is in ESP in time 1 after we invoked foo for the first time with argument 2. And I will explain how to pass arguments today, so don't bother right now. Just let's understand how the stack works. So, okay, we entered the function, right? A is 2, so it's not 0. We decremented a. we're calling foo again, right? But now we're passing 1. Imagine that this line, right, the next instruction between foo and return, and I'm like intentionally, I'm not like putting this address on return because maybe compiler will generate a little bit of more instructions in between, right? We're going to see it later today. Imagine this is label B, right? So since we invoked foo, this B gets placed on a stack, right? And the stack pointer gets changed to this, right? And time 2, right? Or, right? Okay, of course, since we jump to label foo, we start executing foo again, right? At this point, A is 1. It's still not 0. So we again decrement A by 1 and invoke foo with a 0 argument. But again, we do the same invocation. So B will get placed on a stack because this is where we want to return. And ESP will be pointing here, right? Okay, cool. Now we land here with A0. Since we A0, we immediately start returning, right? At this point, let me just change the pen color to blue, so we know we could keep track of it. So, okay, we pop B from the stack, right? We jump to B, meaning that our EAP will be pointing to this B, right? And the stack, of course, will be pointing to here because we forget about this B. This B doesn't get overwritten on the stack. It stays in that memory, so nothing happened to it, but we just forget about it, right? Okay, so we're executing this return instruction, right? And of course, okay, sure, we see that we have to jump to B, change the stack to this position, and again, we'll land on B one more time, right? So again, right, return from function foo again. At this point, again, we're like reaching the return instruction. Since A is at the very top of the stack, we pick it from there, change the ESP to here, and essentially land on A, right? And at this point, we'll continue executing instructions after the foo, which we invoked with a 2 argument, right? Is this clear how this works with recursion? I mean, it's pretty simple, but I just wanted to make sure that we all are on the same page. Any questions about this recursive example? So the stack size is limited. Yes, the stack size is limited. And let me just explain the stack size first. So it depends. Like x6 will be allocating only 1 page for the stack, right? So it will put it here, and it will put something like a guard page here. Guard serves the purpose. If you accidentally keep like passing not like 4, but you passing like 20 salvans here, of course you will run out of space on the stack, right? And at some point you will try to push something into the guard page, and this guard page will not be mapped, and it will result in a page fault. And the operating system will terminate your program saying, okay, we got it, you have a segmentation or like page fault, you're doing something wrong, we'll just kill you, right? For debugging purposes, we can print out what went wrong, right? But you got the point. And of course, different operating systems allocate different stack sizes, but typically in most languages, stacks are continuous, meaning that once you allocated the size, you have to deal with it, and you may run out of stack space. Higher level languages like Rust, for example, might be compiled, and C can also be compiled with support for, I forgot the word, but it's not continuous stacks. Essentially, you can chain multiple stacks together. So that's also possible, but it's rarely done in practice. Rust used to do that, but they don't do this anymore right now. It's arguable whether it's a good idea or a bad idea, right? There was just some pathological case and some benchmark where your benchmark was landing between these 2 stacks and constantly was allocating and deallocating this second chunk, and it was quite expensive, and this is quite a bit of a performance degradation when you allocate and deallocate. If you do it smartly, actually, it's quite fast, but probably they didn't do it smartly. And they said, okay, look, we forget about it, there will be no growing stacks, it will be just 1 stack, and then again some kind of a guard page, and deal with it. If you're running out of stack space, good luck to you. But hopefully I answered this question. So why are A and B not popped? I mean, it just an optimization kind of. There is no real reason, unless you have some security concerns, for leaving, like essentially when your stack goes back here, right? Those values are still there in memory. So there is no real reasons to like nullify them by overriding them with zeros, right? Next time you will be calling functions, you will use the same value, the same addresses, and they will be overridden with something like C, D, and E, for example. And that's okay. So only if you have some security concerns that those values on the stack are sensitive and attackers, for whatever reason, you cannot leak them, then you have to override them with zeros or something like that, right? Does the return have the same functionality like pulp in the previous example? But wait, hold on. We just talked about the red instruction, right? So, yeah, okay. What you're asking is that, okay, we will take a look today and return gets compiled to the red instruction, right? So I missed that. I didn't mention, I apologize. So essentially, yeah, red, this return statement in C is very close to assembly, right? So this return statement in C is compiled to red in assembly. Okay, hopefully everything is good. And now we are on to calling conventions. So, okay, if I ask you a question, so what sort of calling conventions do we really need? Can you tell? Can someone tell me? What do we have agree on about how we invoke functions specifically? Who can tell me? Call by value or by reference. Okay, let me take it by one by one. So call by value, Call by value or by reference is a convention at the language level. So it's not at the level of assembly or application binary interface, right? It's kind of above. So you say, well, in a language, we will be passing values by reference or by value. It's up to the language designers, right? However, this other idea from Surya is the right one. So I don't know, like my finger touches the touchpad and it just, like at this point, it just draws this weird line, which is annoying. So you say order of variables. Absolutely. Which variables though? So you say order of variables. You probably meant to say how do we pass arguments into a function. So imagine we have a function which returns integer and takes a couple of integers like int a and int b, right? The question like, how do we pass those arguments? Do we pass them on a stack or do we pass them in registers, or maybe some of them we pass in registers and some on a stack, right? And this is a calling convention. So the function has to, like, the compiler has to know how to compile the code. So other parts of the system compiled maybe by a different compiler or just even written in assembly, right? By human, like you just handwritten assembly, you need to know how those arguments are passed. Where are they? When you executing the label inside the label foo, you say, okay, I want to access my first argument. Where is it? Is it on a stack? Is it in a register? Stuff like that, right? So this is a calling convention, which is required. And we also need a calling conventions about how we return values from functions, right? Then Shane says, need to know where to find arguments and where to put return value. Exactly, that's what we just discussed. Parameter pushing, call function, return from function. Okay, so a little bit, okay, again, passing arguments. So that's one idea. So order how we pass, essentially parameter passing. But who can tell me more? So what other conventions do we need? Any other ideas? Scope of variables. Not sure what you mean by scope of variables. Callee versus caller convention. Again, a little bit confused here on what Dominic means, but I guess I'll make a guess. So I think Dominic says, okay, we want to agree on who saves and restores the registers. Is it a callee or a caller? Meaning, imagine you have a register, like you have some value inside EAX, right? and you want this value. So meaning that if you invoke a function foo, after the function returns, do you believe that do you have a guarantee that the same value, whatever is there, x, is still inside this EAX register or not? Or maybe it's true for some registers, like maybe it's true for EAX, but not true for EBX, right? And this is the calling convention about whether the callee, meaning that the function itself, has saved and restored the registers to the original values or not, right? And okay, yeah, we need a calling convention about it. So callee versus caller saved registers. That's a good one. And who can tell me maybe the one more, just another one? I'll hint you. Local variables. We need a convention about how to allocate local variables. And okay, I probably like roughly maybe 20% of the class can answer what local variable is, maybe more, and then that's good. But we will cover it in a second. But okay, sure. So just this slide, so essentially enumerates those calling conventions more or less. How to pass arguments on a stack and register, how to return values. And those conventions will differ from compiler. They're not going to differ from optimizations because ABI is fixed, but different operating systems and different compilers, based on whatever they want to optimize for, might choose a different calling convention, which used to be a more common in the past. And now I think a change of a calling convention is more of an exception, because on Unix, if I remember, I would say 90% or 99% of programs will use the same calling convention, which is called Meta-cle on 32-bit machines, and I think it's called System V or System 5 on 64-bit machines, right? So, but back in the days when I was younger, different compilers were compiling code with different conventions. And it's still there. We'll get to the wiki page by the end of this lecture, so we'll look at a couple of them. But let's first look at this Meta-cle calling convention. Let's first introduce this idea of a stack frame. It's a little unusual, so I will explain. You will understand gradually why we need it, right? So, but just bear with me for a sec. A stack frame is kind of an area of a stack which belongs to a single function. So in this case, function draw square invokes a function draw line, and there is a stack frame for the draw square function. That's this area, right, blue. And when we call draw line, we will say that, okay, look, this is a frame, the stack frame for the draw line function, right? And there will be a special register, like we will take one of these general registers, EBP, and it's called a frame pointer or frame base pointer. That's why there is a B here, right? So it used to be somewhat special, and now this kind of like compiler can choose actually any general register. It's just a convention that the compiler will choose this EBP, right? You can use EAX for the same purpose if you want, but fine, it's okay. This EBP will be pointing, well, somewhere in the middle of this frame, but I will explain how it happens, so it will make more sense in a second, right? But roughly speaking, we kind of split the stack into different areas which kind of belong to a function, right? And they are valid for the duration of a function. If we call another function, well, there will be a new stack frame for this new function, right? Do the calling conventions change between 32 and 64-bit assembly? Yes, and I will cover it later today a little. Okay. So how will we maintain the stack frame? To maintain the stack frame, the compiler will generate a special sequence of instruction on entry to every function and on exit, right? On entry to every function, we will save the original EBP, meaning the old value of EBP. We'll push it on a stack, meaning that this is your stack, right? Someone just called this function. So someone invoke call my function here. So what's on a stack? Who can tell me if this is ESP? So what is right here in this slot? Anyone? Return address. Yeah, exactly. So this is the return address, right? And now we're pushing old EBP, meaning that the stack will change and old EBP will be here, right? And what we're doing here is that we're initializing EBP with the current value of ESP, because ESP moved, right? So ESP points here, and we want EBP to point to the same address, right? That's kind of like, you can argue whether it's a beginning of the stack frame, like it's just the value of the EBP register for the duration of the function, because next time we will call a function, the similar thing will happen. Like maybe this inside the function, we will push something on a stack, but there will be again a return value, and we will push EBP on the very top of the stack, and we will assign, and this EBP will be actually like pointing right here, right? Because we will save the old value of EBP, right? And ESP will be pointing here, right? Like I'll show more examples. So if you like, if you're slightly lost, that's just fine for a second, right? So what we pushed EBP and we moved ESP into EBP, right? And when we're leaving from a function, we want to restore it, meaning that we want to make sure that EBP is pointing to the previous value of the EBP. So right before leaving, we will pop it, and this EBP will change to point to whatever was the previous value of EBP here, right? And of course, there will be a return address here as well, right after it, right? And then we can execute ret, because ESP will be pointing at this point right at the return address, right? So far, so good. A little confusing. Okay. Let me stop here for a sec. So ask questions about this, the idea of maintaining the stack frame. Do you understand these two sequences, prologue and epilogue? Yes, no? Yes. Okay, I had 3 yeses, 4, and no nos, 5. Good job. Okay, then we can, for people who are still kind of fuzzy on this, we'll have more examples. But let's move on forward and take a look at how we're going to be allocating local variables, right? Let me ask you an example. So what is a local variable to begin with? Who can tell me? Anyone knows? Exactly, this the variables whose scope is valid for the duration of a function. And the question is like, where is this variable allocated? It's allocated on a stack, right? But okay, it's good, but let's cover other types of variables so we understand, we reliably can understand like which one is which, right? Okay. We have 3 kinds of variables, right? So we have global variables, which are in a global scope, right? And they will be allocated in a special data section. So not today, but I think next time we're going to be covering linking and loading, and we will understand like what is this data section, what is the text section of the program, what is the DSS. But those local variables, the compiler will generate a special part of the program, which will be called a data section. And these global variables, maybe it's like hello here, will be allocated, right? And then when you have to keep them on disk because maybe they're initialized to some values like 17, hello, 25, right? When the program is loaded in memory, so from disk, this data section is loaded in memory, right? And all the pointers which refer to this global data section in memory will be patched by the linker when the loader, if you like, when you're doing the relocation step. So that will become clear next time. But roughly speaking, there is a special section which is called data. And for the global variables, which are initialized to zeros, there is no real reason like to keep zeros on disks, right? Because we know that those are zeros. You need just to have size. And when the program is loaded, we will create this special section, which is called BSS, which is like a short for better safe space, right? It's a joke. I forgot what BSS stands for, but it's a common joke. And so the data will be here with initialized variables where like you will have hello, and you will have 1725, but those will be initialized to just zeros, right? So that's fine. There are some dynamic variables which are allocated on a heap, right? And there is local variables. There are local variables which are allocated on a stack. Again, let's go through a couple of examples to make sure that we understand which one is which. So which variable is this? Who can tell me? It's a global, so it will be allocated in a data section, right? So since it's initialized to hello, it will go to data. If it would be just zero, it can go to BSS, but it's kind of like those guys are similar. What about this guy? It's inside the function. Local. Any other versions? I see some hesitance. No, remember this static keyword is important here. Even if you declare a variable within a function scope, but you say this is static, it's also a global variable. So this world will also go to the data section. It will be allocated once for the duration of the program statically. Okay, that's essentially the same explanation. Now, what about this one? I should change the slide to not to reveal what is this variable. Okay, you probably know it's a, what is it? It's a dynamic variable which is allocated on a heap, right? So the way it works, remember this SBRK system call. So SBRK allows you to allocate a chunk of memory from the operating system, right? By changing your address space. On top of that, you will be running your Meta-cle library. And this Meta-cle library will kind of like keep some metadata, and will keep metadata which allows it to keep track of like which regions of this chunk are free and empty. And essentially when you request a chunk of 64 bytes, it will allocate you a chunk of 64 bytes. If you request a chunk of 65 bytes, it might have to allocate you the chunk of 128 bytes because it only services regions in powers of 2, right? But that's how Meta-cle works, right? So it runs within the process. Once in a while, it requests a larger chunk from the operating system, and then it just keeps track of which area is allocated, which is unallocated, right? Okay, good. And then if it runs out of this chunk, it can request the next one, right? So this is Meta-cle. So it's dynamic variables allocated. This area is called heap, right? Okay, and then the last thing, right, is this kind of variable, right? So remember, I removed the static keyword, so I commented it out. So now it's just a char. And this is one. This one is a local variable, and this guy will be allocated on a stack. And now our goal is to come up with a convention for when and how to allocate space on a stack, right? Okay. Yeah, go ahead.
Yeah, so in that str one, right, can you go back in the heap? Heap one. Yeah, so the str variable will be in the stack and it will only have a pointer to the
correct
heap, right? Yeah, I'm just clarifying that.
Yeah, you're right. So I mean, I'm sorry. So this is a nice detail. So str pointer itself will become a local variable, which is only a pointer allocated on the stack, and this pointer will contain a point. This pointer will contain a reference to the heap area, right, where this 64 bytes will be allocated. You're right, absolutely. All right.
Thank you.
Good, thank you. That's a very smart comment, actually. And I missed it. I should change it probably somehow, or at least talk about it. Okay, so how we will allocate space for local variables. Okay, imagine in this example, we have a function which has 3 local variables, A, B, and C, right? And the reason why we need to allocate stack space on a stack is because we might call this function recursively, right? So this foo calls itself. And so in each invocation, we need a separate instance of this A because it will be different, right? It will be different values. So there will be A for one invocation, which might be like, I don't know, maybe it's X was 0, it's 1. In another function, we call something, since we passed 1 inside, A will be actually 2, right? And so on, right? So for each instance of the invocation, we need a separate instance of A, right? And it's convenient to allocate them on a stack. I probably talked about it before, just because you can allocate them on a heap, like you can have a pointer, but still you need some metadata that you're allocating something in this, like for this specific instance of a function, right? And you can come up with a stack for just some, okay, like it's a little bit crazy. So just let's, you got the point. It makes sense. Okay, cool. So how do we allocate them? So here again, example, 3 integer variables, each of them are 4 bytes. We allocate them on a stack. So how will the assembly code look like? So remember this my function. So we maintain the stack frame, right? Push the old value of EBP on a stack, move ESP into EBP to make sure that EBP points to the current value of ESP. And then we say, look, we will reserve some space on a stack for local variables, right? So the stack will look something like this right now. So there will be a return value, there will be EBP, which we pushed, right? ESP is pointing here, EBP is also pointing here, right? And then we say, we want some space for local variables. So stack grows this way, meaning this is address 0. So what we're doing, we're just subtracting some number of bytes from a stack, right? So in this example, we need 12 bytes because we have 3 4-byte integers, right? So roughly speaking, one will be here, another will be here, and this one will be here. We're doing that by just setting ESP to this address, right? EBP stays, EBP doesn't change for the duration of the function. It just marks where the frame, I can say starts, but it's arguable whether it starts at local variables, but yeah, I would say it starts here, right? Got the point? And when you leave from the function, of course, you have to free local variables, right? So you have to deallocate them. So in this example, you can deallocate by, again, adding something to the ESP. In this example, the code essentially deallocates local variables by just resetting ESP to the value of EBP, because you know that this is how ESP was when you enter the function. So if you want to forget about this, you just reset it back to this. At this point, you can pull back EBP, maintain your epilogue, and return, right? Because the return address will be at the very top of the stack, right? But the whole idea is to just essentially subtract some number of bytes and make sure that this space is reserved on the stack for local variables. So here is an example. So again, so the same function, A, B, and C, we subtracted 12 bytes concretely. And this is how we can access those variables, right? Because remember how the stack looks like again. So my lovely return value, my EBP, and then you allocated space for 3 of them, right? So one of them will be EBP minus 4, because this is where EBP points. EBP points here. And this guy is 4 bytes, right? So that's why you have to subtract 4 bytes to get on the beginning of this value. The other guy is EBP minus 8, because you want to subtract 8, right? And the last one is EBP minus 12. So this is where you have like 2, hold on, I don't know, we didn't initialize them, but, okay, this is the code which actually initializes them. So essentially, this is the code which says C is actually equals to 2, B is equals to, hold on, 5, and A equals to 10, right? Okay, got it? Any questions about this? Let me just, I have this animation, but that's the end of it. Essentially, I explained it was a drawing. We're good. So we push onto stack from left to right. The order of variables, yeah, that's a good question. I think you get in the order of initialization. So this is A. So A gets allocated here, right? Then this is B and this is C, right? because it's 3 variables. If you have another here, int d, d would be allocated next, right? So you kind of go in the order of, like, if in the order of how variables are introduced into the scope, right? Okay, that's good. We got how to allocate variables, like local variables, right? Now, the question is like, how will we pass arguments into the function? So there are literally 2 options. You can pass in registers, or you can pass on a stack, right? I mean, you can, in exotic systems, you can say, look, I can pass one pointer to something what is called a message, which is used in microkernels. And it's just one argument in one register, for example. It's a different calling convention. And inside the message, you will have some arguments, right? But this is not how it's typically done in normal C code, right? So literally 2 options, either in registers or on the stack. And x86 32-bit version and 64-bit version does it a little bit differently. So 32-bit code passes all arguments on a stack. Nothing is passed in registers. Everything gets pushed on a stack. But 64-bit version does it slightly different. It passes the first 6 arguments in this order in registers: RDI, RSI, RDX, RCX, R8, and R9. And then the other arguments, if you still have more than 6 arguments in a function, will be passed by pushing them on a stack, right? The return values, however, will be returned in the EIX and EDX registers. And most of the time in C, you return just one value. So if it's an integer or some other thing, then it will be placed inside EAX register. If it's a pointer, like, I don't know, char pointer, which foo returns, or some struct pointer, it will also be placed in the EAX register. I actually don't really know in what case EDX is used. So I should actually go ahead, or you go ahead and figure it out for me. Post it on Piazza, tell me, okay, under what condition C actually generates codes which uses EDX. So I honestly don't know. But fine, and 64-bit version does the same. So 2 registers, RAX and RDX. But normally it's always RAX, right? So RDX used in some weird cases. Is it in the cases where multiplication takes place? But if you multiply something, you still return just one number, right? It just doesn't matter. So I honestly don't know. We have to double check. Okay, cool. Let me give you an example. So you have a function. Very long number, yeah. Yeah, sure. And then it's a floating point value. It will be passed in a floating point register or on a stack. There is a calling convention which covers how to, this calling convention actually covers how the floating point registers are passed as well. Just I'm not touching on that in this class, but I will link to the Wikipedia page for you. 3 arguments, int x, int y, int z. So what kind of code will get generated? So example invocation 2, 5, and 10, right? So you push them on a stack before calling a function. So you first push the last argument, 10, then you push 5 on a stack, then you push 2, and that's the order of the arguments in this specific calling convention. It can be different in a different convention, right? And then you call a function, right? So your stack will look something like 10, then 5, then 2. Since you call a function here, there will be a return value here. And then that's the ESP when you just enter the function. If you're maintaining the stack frame, EBP will be pushed here, right? And here will be the space for local variables. Again, in this example, stack grows this way, right? So kind of easy, right? So nothing super hard. And this is how you can, this is example stack, which illustrates how you can access those arguments from within the function. Everything is relative to the EBP, right? So remember, this is the return address, and then we pushed EBP, right? So stack grows this way in this drawing. EBP points right here. So your return address will be EBP plus 4 because this is address 0. This is your max address, right? The first argument will be EBP plus 8. The next argument will be EBP plus 12. And then the third argument will be EBP plus 16 because each of these entries is 4 bytes, right? And your first local variable will be EBP minus 4, right? Because you're going down, right? So EBP is here, right? And so on, EBP minus X, your X, like it's X, which is X multiplied by 4 if it's your X local variable, right? Is this idea clear? Elliot says that he knows that EDX stores the remainder of in unsigned division. Could that be it? Unlikely, but can be. I don't know. Let's double check. You're in charge now, Elliot. You go and search, Stack Overflow and other resources to find out the answer and tell us on Piazza. Okay, cool. And if not, I will find it. Here's another example. So this is how the code looks inside the caller function, right? So there is there are two functions here, caller and a callee, right? The caller function calls the callee. So first, you're preparing the call site, right? Because your goal is to call this function, right? Passing 3 arguments, 1, 2, and 3, right? So inside the caller, you will obviously maintain your own stack frame, right? So you will push EBP, save ESP into EBP, starting the new frame. Then you're going to go ahead and push 3 arguments, 1, 2, and 3 on the stack, right? So that's it. Then you start calling the callee, right, with a call instruction. And then when you execute the callee, you can come back. What you need still to do is you have to remove these arguments from the stack, right? Because you pushed 3 4-byte arguments on a stack, right? You have to forget about them. And I said that you can forget by simply adding something to the ESP, right? So you're adding 12. That's good. And then you just use a subroutine result because, okay, whatever gets returned here, red, you add 5 to it. You restore the old call frame, right, by popping EBP, right? And then you return, right, with this red instruction, right? Let me ask you a question. Where is this red? Why don't you do anything with the red? Red int red local variable, which is inside the caller function. How do you return this value? It's already in EAX. Exactly, Elliot, right? And you can. Yeah, exactly. Look, the compiler is smart enough. So this function returns something in the EAX register, right? We added 5, and it still, since addition, like leaves it inside EAX. And we're using EAX as the return value. We don't have to do anything. We just return because the return value is already inside EAX. So this is kind of clever in this specific example in which this variable, by the way, local variable optimization, it didn't allocate space on the stack. They just said, okay, look, we're going to place it in a register and that's it. Forget about it. So compilers are free to do that, apparently, right? So, and that's smart. And we will, if I will have enough time to show the examples, we'll take a look at different optimization levels, and we'll see that, like, if there is no optimization at all, not even O0, there will be a like value allocated on the stack. We'll be like saving and restoring stuff from it. But really, just EAX is a good register to put this local variable, right, in this specific example. Does EAX get reset to its original value before function call and return and after return? No, there is nothing happening. Call instruction doesn't do anything to EAX, but we'll get just in a second to another calling convention which covers callee saved and caller saved registers, and you will understand maybe what happens to the registers. But really, in this function, that's all body of the function, right? It doesn't do like it says, I don't care what was inside EAX. I will use it for my own purpose, right? Because it's actually a caller saved register, so I don't have to save it and restore it, right? I will just like override it with this return value from this function, and then save something again here, and then return it, right? But let's get to this. Let's actually get to this calling convention, which covers who caller or the callee has to save the register. Let's get to it in a second. So just wanted to give another example. So the code inside the callee, right? So inside the callee here, we, again, since we looked at it before, we're allocating space for 3 local variables, right? By subtracting 12 on the stack. And then we actually, what we're doing here is that we say, look, now you can refer to these local variables by using EBP. So essentially EBP plus 8, EBP plus, those are actually arguments, not local variables. So EBP plus 12, EBP plus 16. and you can refer to local variables either by using EBP minus 4, or using ESP plus 8. Similar, this one is EBP minus 8 or ESP plus 4, right? And if you look at the diagram for the stack, you will understand that those equations correct, like those addresses are valid, right? It's very easy to understand. Okay, but what I wanted to say, we obviously, before leaving, since we allocated space here, we have to deallocate this space, right? Then we will restore the frame and return, right? And I wanted to make a note here that x86 has a special instruction for this, for restoring the value of the stack before deallocating essentially local variables, if you want to deallocate this way, and popping the EBP. This instruction is called leave. You might see it once in a while, but it's not frequently used, right? So often it gets optimized out, right? But just make sure that you understand that leave is exactly the same as these two instructions. Okay, I wanted to talk a little bit about this. I kind of introduced the stack frames, right? And we kind of swallowed them. We said, okay, look, got it. We're gonna be using them. But why do you think we really need them if we read them at all? What do you think is the reason for maintaining the stack frame? Maintain the structure between function calls. In a way, yes, but it's hard to say what you mean by that. It would be nice if just like isolate functions from each other. No, really, there is no isolation. One function can say ESP plus 128 and access whatever it wants from another stack frame. It can actually inspect the stack and see how it was called from which other function, because if it can find the return value, it could say which function called it, right? Easier to maintain hierarchy when functions call other functions. It's not that straightforward. Okay, let's read this comment from the GCC manual. The thing is that this stack, maintaining the stack frame is optional. And GCC has a flag which says omit frame pointer, meaning generate code without the stack frame pointer, right? And what it says don't keep the frame pointer in a register for functions that don't need one. This avoids the instructions to save, set up, and restore frame pointers, meaning it will save you a little bit of time, because when you do this, when you do push EBP and then move EBP, move ESP into EBP, remember push takes 2 to 3 cycles because it touches L1, first level cache. Move takes 1 cycle, right? And then here, when you essentially you do a pop EBP, it's yet another 2 to 3 cycles, and then you return, right? So you're kind of saving whatever, like 3 to 5 cycles here and 2 to 3 here. So the total is 5 to 7 cycles, right? And now again, if you like the knowledge of assembly can tell you, okay, how much you're gonna be, how many cycles is a simple function invocation, right? So, and you can say, look, the call instruction pushes something on a stack, right? So it's like 2 to 3 cycles, and return instruction will read something from the stack, so it's 2 to 3 cycles. So the empty function call invocation is at least like 4 to 6 cycles. I mean, compilers and CPUs can execute multiple instructions in a row, and it's a good experiment actually. Like we should add a homework which actually measures how many cycles an empty invocation takes. I would say it will, like, at some point it will saturate the CPU. It will still be like 4 to 6 cycles. But here you will add seven more cycles, right? So because you're maintaining the stack frame, right? And it matters. I mean, it depends on how frequently you invoke functions. If you have a code which has a lot of many small functions, then you will have to maybe it's like 10% of your execution time, maybe 5%, maybe 2%, but still it matters. And that's why actually this flag is on by default in modern systems. When I taught this class before, in like 5 years ago, it was off. The compiler was generating the code with the stack frame pointers, at least on 32-bit machines, but now it's on. So it's like the compiler by default will not generate the stack frame pointer. So someone says F omit is a typo. F means a flag here. F stands for the flag. Flag minus F, omit stack, omit frame pointer, right? However, it also makes an extra register available in many functions, right? Because right now EBP is used by, it's occupied by the pointer to the stack frame, right? And it's, how many registers do you have? You have 8 total, right? But one is ESP, so one is gone. So you have 7, down to 7. If you're using EBP, you're down to 6, just only 6 general registers. So the chances of seeing a register spill, the case in which you say, look, I have to really like push something on a stack and pop it later because I'm running out of register, the probability of it increases in different kinds of code, right? So that matters as well. So it will also like save you two cycles to push something in 2 cycles to restore, right? However, this comment is important. It also makes debugging impossible on some machines. What it means is that we're maintaining EBP for humans, essentially. Let me give you an example. Imagine you enter a function and you're passing an argument, right? If you don't maintain the stack frame, when you enter the function, the address of this argument, right, is ESP plus 4, because ESP is pointing to the return address, right? I agree with this. But as you start executing function, maybe you push something on the stack. Maybe you allocated local data. Maybe you just pushed because you needed like to save a register, right? And suddenly the location of this argument changes, is no longer ESP plus 4. It will be ESP plus 8 or ESP plus something, right? Compilers can keep track of this, right? And they can say, okay, look, I know what happened. I know where the arguments are, but it's hard for humans. For humans, it's always easier to say, look, if this is my return address, if I saved EBP here, old EBP, and EBP is currently pointing here, so this argument will always be EBP plus 8 for the entire duration of the function. No matter what you push on a stack, ESP changes, but EBP doesn't, and it helps a human. It's also very easy to construct a backtrace because you know that right above the EBP, there will be a return address, right? And you say, look, I know that foo called internally bar, and foo got called from main, for example, bar called internally buzz, right? And those values will be there on the stack, right? Because you say, look, every time I save EBP, there will be a return address right above it. And my old EBP will lead me to another stack frame where I find EBP, previous EBP, and return address right above it, right? So I can very easy to build this, the backtrace, right? Compilers can still do that. They can include enough debug information in the binary saying that at this specific location, we know where the return address is in the stack, where the local arguments are on the stack. So we will help you, we will print out the backtrace. For humans, it becomes harder. So you have to really understand what's going on in the program. And that's essentially the reason why EBP is maintained. And inside our version of Exhibit 6, we will enable it with EBP. We will maintain the stack frames, meaning that our debugging will be simplified. So you can always print a backtrace. There might be even a homework which asks you to print the backtrace. And in general, inspecting process will be easier, right? So this is called stack unwinding or backtrace, right? Did you get this point? These arguments for maintaining the stack frame. Okay, cool. Let's keep going. And roughly speaking, again, on 32-bit machines, you save a lot of registers, right? So like I gave you kind of the algebra or like the equation for how many cycles you save. I want you to remember this, and I want you to start reasoning in terms of cycles as well. It might matter, you know, if it's like 1% of your performance, but imagine you're running a $1 billion data center. So 1% out of $1 billion, it's still a sizable amount if you can somehow extract this 1% of performance, right? $1 billion a month, obviously, right? And on x86 32-bit version, you only have 8 registers, right? So you lost one because it's due to stack, and another one is EBP. So it's like roughly 14% of your register space. But on x64-bit machines, which has 16 registers, it probably really doesn't matter. So only this has your performance impact, right? And that said, GCC actually sets to on this flag, a mid-stack pointer, at any optimization level. The moment you have -0, you will get it, right? 01, 00, 02. So don't get surprised that if you don't see the stack frame, it's because this flag is on, and you can actually set equals to no, right? I'll give an example, maybe not today, but next time, for how to control it. Okay, so far so good. And this is a relevant part of the GCC manual. So click here. Again, I argue you to essentially learn how, if you didn't start, but fine. So if something is like going on, go ahead. I wanted to actually click it. Okay, yeah, here it comes up. It didn't come up again. Maybe no. Why is that? I clicked it. Okay, now it comes up. So just make sure that you can read the GCC manual and understand what at each level of optimizations, which flags are on and off, right? And one of them is this maintain stack frame pointer, right? So just get into it, like make sure that it's hard to understand many of these flags, and I don't know many of them, but at least that's the beginning. So just if you really need something, like optimize your code carefully, extract last bits of performance to just understand what GCC is doing. Okay, the last final bit of this convention is who saves and restores the registers. So remember, when we call a function, the processor doesn't really save and restore any of the registers, right? Nothing happens. It's just the call instruction. We just push something, we push the return value, which is A on the stack, and then just jump to this label foo, right? That's it. Nothing else happens. And we need a calling convention, whether the callee, like essentially what I'm talking about, as I said. So imagine you call a function foo, and you had some value inside the register, EAX. The question, do you expect to have this value the same after you call foo or not? It will be some trash. If it's some trash, then what you have to do, you have to push EAX on the stack and then pop it back, right? Meaning that you saved it here, you are the caller, right? You saved the register and then you restored it. So it's called the caller saved register. And if the function will do that for you, meaning that some registers will be saved and restored by the callee, then it's okay, you don't have it. Like some other registers, and I don't remember which ones are callee saved, but they will preserve their value, retain their value across the function invocation. Okay, so in C-DECL conventions, registers EAX, ECX, and EDX are caller saved, meaning that if you want this register after the function invocation, you have to push it on the stack and restore it, right? And the rest, other registers are callee saved. So for example, if you have a value inside EBX, right, you call a function, you know that EBX here will stay the same, right? Just because if the function foo uses this register inside, it wants to do something like move something into this EBX register, right? It has to push it on the stack and then pop it, restoring it, right? Preserving it across the function invocation. So this is a callee saved register. And right, so because callee, the function itself has to save and restore it, right? And that's it. That's it for the callee conventions. And the convention which I described today is called a C-DECL or C declaration. And there is a Wikipedia page which will lead you to the other calling conventions which exist here, right? So essentially what up. I actually donated already, but fine. I mean, I have a monthly donation, to be honest. But what happens here is the following. So look, Meta-cle is a calling convention that originates from Microsoft compiler for the C programming language, right? So it says in Meta-cle, subroutine arguments are passed on the stack. This is exactly what I explained. Integer values and memory addresses are returned in the EAX register, right? There is also a bit about how the floating point registers are passed and returned, right? Registers EAX, ECX, and EDX are caller saved, and the rest are callee saved. The floating point registers ST0 to ST7 must be empty, hopped or freed when calling the new function, and ST1 to ST7 must be empty when exiting the function, right? So it's again a convention on what you can leave inside those registers, right? And if you wonder what other conventions are there, there is a whole table here, which essentially describes you all the conventions which are currently popular or exist on 32-bit version of x86 architecture. So Meta-cle is used by the GCC and the Microsoft compilers, right? Here again, we like back in the days, this Wacom compiler was popular, and it was using registers to pass arguments. Like the first 4 arguments were passed on this in registers, and the rest was passed on the stack. And the Meta-cle, no arguments are passed in the registers, but only everything is passed on the stack, right? And for example, in 64-bit version of this convention, which is System 5, right? Those first 6 registers, first 6 arguments are passed in registers, and the rest are passed on the stack. And also some MMX registers are also can be used to pass MMX arguments, right? And also, if you just telling you how to read this table, right? And if you care about it, you can go and read more. Just make sure that you understand what's going on. Essentially, x86 64-bit, a slightly different convention. Multiple conventions exist, but you know, like Delphi compiler was using a slightly different conversion here, convention on 32-bit versions. And on 64-bit versions, you know, everyone kind of converged to a single convention. And the reason for why those conventions existed is that optimizing different cases, like passing a couple of registers, a couple of arguments in registers, will save you a couple of instructions which you use for pushing those arguments on the stack, right? But on the other hand, you like losing those registers, right? So if you really had some valuable data in these registers, you have to save them on a stack and then pass them, right? So it's a trade-off, and it's probably they converge to something what is meaningful today, right? So okay, cool. At this point, let's probably stop. I will stop here for final questions. We're 4 minutes over, but I'll hang out here answering for a little bit. Why EBX are not designated as caller saved? So the balance here is that, obviously, okay, so EAX and EDX are caller saved because they will be overridden by the callee, since their EAX has a return value, right? And EDX also can have return value. ECX essentially is just one register, which is caller saved, right? And the others are callee saved. And I think, I mean, I actually don't know the exact answer, so that's a good question. I believe that they're trying to strike the balance between use cases in which the compiler can generate the code which minimizes the number of like essentially saves and restores of registers on the stack. So in this specific example, they say, look, I have my EBX and other general registers available for the caller. If the caller can call a function foo, it doesn't have to save and restore them, right? So no overhead. Inside foo, right, you have 3 registers which you can use without worrying, like it's yours. You don't have to like save and restore anything. And maybe, you know, it's enough to like, for many computations, it's enough to use just 3 registers and then use it, just simply return in EAX, right? red, meaning that EAX is there, right? And again, you saved, you didn't push, you didn't pop anything on a stack, right? So it kind of strikes the balance, giving some registers to the caller and some register to the callee, right? And like that makes sense to kind of split them roughly in half to have this balance, right? That's my understanding, at least. Any other questions? Oh, there's a class at 6:30. Yeah. You should, like, I'm sorry, like, when will we need EDX to store return values? I don't know. We'll figure it out. But okay, so since people are asking me to stop, I will stop. And if anything, I will start my office hours next week. And you're welcome to come and ask all these questions as well. And thanks a lot for your time and good luck, guys. See you. What is it today? Yeah, see you what next week then. Next week we'll start doing linking and loading. Thank you.